So, dear colleagues, we have the final talk of our conference program for today. And the final speaker is Krishnendu Gongopadhyay from the Indian Institute of Science, Education and Research from Mohali, India. So, Krishnendu, you can start, please.
Yeah, so thank you, Nikolai and Andrei and all Russian friends to invite me to this nice conference. Yeah, so there was some confusion regarding schedule of my talk because I mixed up Indian time and Russian time, and that actually created confusion, and accordingly my lectures were swiped and then swiped back to the original plan again. And I thank Nikolai for for his patience to go through this confusion and settle it. All right. So I would have been happier if I would have come to Russia to attend this conference, but nevertheless, something is better than nothing. Now, in this talk, as you might have seen that the topic of the talk, I must apologize to the knot theories that it may not be directly related to knot theory as such, but it is something related to the group theoretic part. As I have mentioned in the abstract, that the modular group SL2Z, I mean, you can think of it as something related to the braid groups. So in that sense, it is connected to this conference. But however, I will not be speaking about modular group, but what I will be more focusing on will be something that is called Hecke groups. And it is also broadly, broadly connects to knot theory and braid groups in some way. But the viewpoint that I will be discussing today is very much group theory. So let me first define the Hecke group. So the Hecke group, I denote it by gamma P, is a Fuchsian group. Fuchsian group means discrete sub, I will maybe write it down. Discrete subgroup of PSL2R, which is generated by the maps. So there is a order 2 map involution, and there is a translation by cosine pi by p, and we take p greater than equal to 3. So geometrically, gamma p is isomorphic to Z2 to the free product of Z2 and ZP. And when you take gamma 3, that is PSL2Z, which is the modular group. So this is the prime object of my talk here. Now, the problem that we are interested, is a kind of broad theme. So the theme of work here, theme of the work, is a broad theme of work. It's called, is to classify reversible and strongly reversible elements in groups. Now I just mention, so take a group G, G in G is reversible or real, or we are also calling it reciprocal. I will tell you why. Reciprocal if G is conjugate to its inverse in G, and it is strongly real or strongly reciprocal or strongly reversible if G is conjugate to G inverse and H square is identity. That means it's conjugate to its inverse by order 2 element. Now, in this case, G is also product of 2 involutions. Okay, so that means every strongly reversible element is real, but the converse is not true. Now, in the literature, there are many works for classical groups where equivalence between these two notions have been studied, but concrete list of reversible and strongly reversible elements, at least we have not seen anywhere. It's not very, I mean, it has not been addressed other than finite groups. So recently, with my collaborator Chandan Maiti and Tejbir, we have we have counted reversible and strongly reversible element for several linear groups where K is, real, complex, or the quaternions, mostly in linear Lie groups, I would say, general linear and special linear Lie groups, and also in affine groups over K, which is GL, NK, semi-direct product Kn. All right, so these are some of the work where we have explicitly listed all reversible and strongly reversible elements. But this is not the main topic of my talk here. It's just a comment that I made here. So now, why one should study strongly reversible elements? Now, definitely, I mean, that's, if something is strongly reversible, it's a product of 2 involution. That is one aspect. But, there is another aspect that if you have a group G, so if you have a group G, and you take a element, so take an infinite order strongly reversible element H, okay, then say RH R inverse is H inverse. So that means RH is an infinite dihedral subgroup of G. So when one explicitly classify all reversible and strongly reversible elements, that implies classification of infinite dihedral subgroups of G. Now this is connected to geometric setup. So you take any take any Fuchsian group G. So when G Fuchsian, the infinite dihedral subgroups, assuming that this element 8 is primitive, they are in one-to-one correspondence with the primitive reciprocal geodesics in H2 mod G. All right. So a geodesic is reciprocal. That means it is equivalent to itself, isometric to itself when the orientation is reversed. All right. So now this is the geometric motivation, and it is connected. When G is modular group, it is connected to theory of automorphic forms, and with that motivation, Sarnak, Peter Sarnak, he parameterized and counted reciprocal classes for modular groups. And on the other hand, reciprocity in modular group, I mean, it's a very rich problem. It has been addressed from many other viewpoints as well. So there is a beautiful article by, for example, John Conway, where he has used combinatorial theory of certain graphs to classify these reciprocal classes in modular group. And there are also number theoretic, kind of viewpoint using Gauss's quadratic forms. One can also address this problem. Then there are dynamical aspects when you look at modular group as automorphism group of the torus. One can use theory of continued fraction and things like that to address this problem. So there is a nice survey for reciprocity in modular group in a book by O'Farrell and Ian Short, called Reversibility in geometry and dynamics. So it is in the chapter 7 of the book. All right. So this is roughly the picture why we were interested in understanding this problem for Hecke groups, because we thought it's a very natural problem to ask this question for Hecke groups, which are generalization of the modular groups and which are also Fuchsian groups. Now, our main is to classify the reciprocal classes in the Hecke group, and we wanted to sort of generalize this count by Sarnak. At least the Sarnak has also given nice estimates using analytic theory of kind of spectral theory, but we don't. We are not very familiar with spectral theory, so we thought we will at least take out the algebraic part of his count and parameterization, and we will try to generalize for the Hecke group, and that's what we have done. But before that, one can more generally ask, what about a Fuchsian group, about reciprocity in a arbitrary Fuchsian group, which is not very difficult to say, and I don't know whether it is very well known or not, but we have never seen it. But it might have been known to experts. Well, I don't know, but here is the result. We have proved it in our paper. It's a joint work. Yeah. So this whole thing, whatever I will speak for the next 10-15 minutes, is a joint work with my student Devattam Das. Okay, so the first theorem that we have observed is the following. So let gamma be a, so I am assuming little bit of uh, you know hyperbolic geometry here because it's only very short talk, but anyway, so let gamma be a Fuchsian group. Then the first observation is that an element G in gamma is, so we will, in this rest of the talk, we will call reversible element as reciprocal, following, Charnak's terminology. He called reversible elements as reciprocal because it corresponds to Gauss's, I think, reciprocal form. So that's why probably they called it. I don't know. But anyway, so I will call in the rest of the talk reversible elements as reciprocal. All right. So an element G in gamma is reciprocal if and only if it is strongly reciprocal. And something more happened. Further, the reciprocators, that means the element that conjugate G to G inverse of a reciprocal element are involutions. So in a Fuchsian group, in general, in a group, an element G is reciprocal. I mean, there are many groups where an element G is reciprocal if and only if it is strongly reciprocal. But the conjugating element of a reciprocal element need not be always involution. I mean, there are examples, for example, in general linear group or special linear group, where you can find out, you can exhibit one conjugating element, which is not involution, but at least one involution is there. But for a Fuchsian group, whatever element conjugates G to G inverse, they are all involution. So there is no difference between reciprocal, strong reciprocal, etc. Because whenever you want to conjugate one element to the other, you need one sort of rotation. It's a kind of a rotation through an angle pi, and so every reciprocator is an involution. And the second thing is that the only possible reciprocal elements are either the hyperbolic elements, that is conjugate to Z goes to RZ in PSL2R, or the order 2 elements. So this has reduced our problem to just to understand the hyperbolic elements for Hecke groups. Okay, so now we want to define some invariant here. All right, so let me define one. I want to state the main result before getting into further. So let me at least give you the classification for reciprocal elements in a Hecke group. So definition. So let A be a hyperbolic element in PSL2R. All right. Now whenever you have something in PSL2R, then you can, SL2R to PSL2R, there is a 2-to-1 map, right? Which is the projection map, because every element in PSL2R is the SL2R modulo plus minus identity. So we denote one of the lift as ABCD. All right. Yeah. So now we define something which is like cross ratio, but it is not cross ratio. We call it, we define the fixed point ratio of A by theta of A, which is, you see, we have this matrix A, B, C, D. So we just take B minus C by A minus D when A not equal to D. If A equal to D and B not equal to C, we define it to be infinity. And if A equal to D and B equal to C, then we define it to be 1. All right. So it looks strange at the beginning. What is this quantity? Now, here is the interpretation, geometric interpretation of this quantity. So every hyperbolic element A has exactly 2 fixed points, U1 and U2, on the boundary circle of the, on the boundary of the hyperbolic 2 space. Okay, fine. All right. Now, what are these? So in the nice case, when A not equal to D, or even when A equal to D, B not equal to C, theta A turns out to be this quantity. So where U1 and U2 are the fixed points. So it's a ratio. It's a kind of ratio of combination of fixed points. So it's a kind of, we identify del H2 with R union infinity. So you can add and subtract fixed points, and you can get this equivalent formulation of the fixed point ratio. And when we have the degenerate case, okay, sorry. We have the degenerate case, B equal to C, then this fixed point ratio, so theta A is just a fixed point for A. All right. Now, from these two, whatever we have written, a nice, interesting fact comes out that theta A is an invariant for the cyclic group generated by A. So this is kind of invariant of the cyclic group. That means it does not change under iteration of A. Now, with this definition, now we are ready to state one of our main results. So I mean, we have also given one parameterization of the reciprocal element, but I will not talk about it. I will only state this result here. So this is again with Devattam Das. Okay, so for the Hecke group, the following are equivalent. So first of all, E is reciprocal. Then there are two cases. First, P odd. E is either an involution or conjugate to a hyperbolic element H such that the lift of H in SL2R are symmetric matrices. So here we don't need fixed point ratio. For P even, D is either an involution or conjugate to a hyperbolic element H such that the fixed point ratio of H is either 0, 1, or cosine pi by P. So this is the classification of reversible elements. Now, when P odd for modular group, the same theorem is well known, and Sarnak also proved a version of this theorem. But for P even, it was not observed. I mean, for other P and for P even, it was not observed before. Now, one question one may ask that you know, I mean, yeah,
I apologize. We finished our time.
yeah.
Can
So
you
just
please go to the concluding remarks?
yeah, absolutely. Yeah. So so that's the classification of the reversible elements. And another thing is that actually we can actually, using the fixed point ratio, when A is hyperbolic and suppose theta of A is eta less than 1, then one can actually explicitly write down the reciprocator phi as 1 by 1 minus theta A square theta A 1 minus 1 theta A. And using these tools, we may also we have also parameterized and kind of given a finer understanding of the reciprocal classes as well. So with this, I would like to thank all of you for your attention. Thank you very much.
Thank you. Let us thank the speaker. We really have time for one short question, if there is one. If there are no, so I suggest to thank Krishnendu again. Thank you.
Thank you very much.